Hello, welcome to today's presentation. Today's presentation is about exploring the climate, groundwater, wetland axis using the convection permitting model. First of all, I want to thank my collaborators from University of Saskatchewan, NCAR, and Ducks Limited Canada. The study region is the Prairie Pothole region, located in the center of North America across Canada and US. In the Prairie Pothole region, there are millions of these small wetlands, also called potholes. These potholes have very important ecosystem services, as they can restore carbon, regulate floods, purify water resource, and are important habitats for migrating waterfowl. And this is the motivation of today's study. However, the climate, groundwater, and wetland interactions are important and very complex. The figure on the left shows a diagram of the three components interacting in the wetland landscape. The climates will impact on the groundwater through precipitation and snowmelts that can impact on the groundwater recharge. And the evapotranspirations will decline water table depth in the summer. The up and down of the groundwater dynamic will reflect on the surface water extent through wetland through supplies of two-way interactions of soil moisture and groundwater. And finally, surface water in the wetlands will feed back to the atmosphere, altering surface energy and water balances, inducing a cooling and moisturizing effect. And it is important to use a convection permitting model for this study is because the very fine, very small scales of a wetland feature requires high resolutions for surface heterogeneity, as well as the reliable meteorological forcing, especially precipitation. And that's why we need to use the convection permitting model. The first step of this study is to look at the climate variation impacts on groundwater dynamic. To do this, we apply the 4 kilometer swath simulations conducted in NCAR group on the contiguous US, and we focus on the black box in the Prairie Pothole region. We use the 4 kilometer meteorological forcing and run the land surface model for 13 years with 2 groundwater schemes. As you can see, the figure below shows the 4 kilometers swath simulations have significantly reduced precipitation biases comparing to a 32 kilometers precipitation biases for a reanalysis data called NOD in the same region. The 2 groundwater schemes we're going to look at is one is the runoff option number 1, that is only simulates the downwards water flux from soil moisture to groundwater due to gravitational drainage. However, in this region, that the two-way interactions, not only the gravitational drainage, but also the capillary effects is very important in this region, especially when the water table is shallow that can interact with the 2-meter soil columns in springtime. And this option is referred to option number 5 as the shallow groundwater scheme. So now we're going to take a look at how is the groundwater number 5 schemes will simulate the capturing the interannual and seasonal groundwater dynamics. We pick 11 sites from the Prairie Pothole regions, and it looks like the number 5 schemes has reasonably captured interannual and seasonal groundwater dynamics as the recharge timing in the springtime of the groundwater table rise and then decline due to evapotranspiration in summer. Another aspect of evaluating groundwater is to look at the groundwater terrestrial water storage comparing to a global remote sensing product of GRACE. That the GRACE provided terrestrial water storage, TWS, and a monthly anomaly. Basically, it is the water mass on the surface. You can see that the option number in the grace period, it is an increasing water anomaly in the Prairie Pothole region. For the two groundwater scheme can successfully simulate this increasing trend, while option number 1 will underestimate its amplitude and interannual variability, while option number 5 has a better simulation of the TWS phase and amplitude. However, it will overestimate its variability and anomaly. Now, the second step is to look at how the groundwater dynamics will affect the surface water extent. Traditionally, the Lancers model will have a concept of the top model is a redistribution of the water table depth and soil moisture and then generate an area called F set. The F set is a fraction of the grid cells that is saturated, and the waters from precipitation will generate directly to runoff in the F set portion, and the precipitation on 1 minus F set portion will drains underground, become infiltration. These F set in the top model concept is simulated as an exponential function of the water table depth, as you can see on the right here, that the F set is equals to a F set max is a parameter times an exponential function of an F times the water table depth minus 2 meters the soil column depth. So we can see that in many of the Lancers model, the F set max equal to 0.38 and then F equal to 6 is a global mean values in many of the models. And this F set is usually used as an index for wetland for many of the models saturation evaluation. So now we're going to look at how will the model simulate F set diagnostic comparing to a remote sensing product in the prairie pothole region. You can see on the top is the GIEMS, is a global inundation extent from multiple satellite products from 25 kilometers resolution. And on the bottom is the NOAA-MP model simulate F-set extent on the base of exponential function of water table depth. You can see the maximum extent, the NOAA-MP model would underestimate F-set, while the minimum extent will overestimate it. The minimum extent for the mean extent is relatively comparable. I will show you why this model simulation diagnostic is so different. If you look at the time series of the monthly mean wetland extent and water table depth, you can see that the blue dots are representing the remote sensing index, while the F-set red lines are from the model diagnostic. You can see that for the maximum value, it is model is underestimating comparing to remote sensing in the spring and summertime. And while in the winter time, the model are overestimating the minimum value in winter time. And you can see that the water table depth has an increasing trend, while the remote sensing doesn't show a very significant trend throughout this 13 years period. And the reason why the model using F-set concept is not a good indication for the water table, for the wetland index is because maybe is the freeze and force of the soil ice will prohibited exchange of thermal and water between the surface water and groundwater. So if you look at the figure on the left, I'm showing the 4 layers of soil ice and soil water corresponding to the remote sensing index. You can see in the winter time, when the remote sensing index is almost throws 0 and the soil ice is high. And while in the summertime, the soil water has a very good correspondence with the remote sensing index. And if you go deeper into the soil layers, these signals is not as clear as the first 1 and 2 layers. So we think of an idea not representing the F-set as a function of water table depth, but modify the parameterization of F-set based on soil water content on the equation on the right. And you can see the figure that the green dots are showing the new functions of soil water stress, and then comparing to the FSAT value, comparing to the remote sensing indexes. On the next step, is look at how we are doing. Finally is trying to incorporate the surface water extent, comparing surface water storage into the NOAA-MP LANDSAFES model, and finally study the feedback from the surface water to atmosphere. You can see on the left is the default NOAA-MP setting, where 1 minus FSAT portion of precipitation goes to drainage, and FSAT portion will directly go to runoff. And on the right-hand side, first we modify the FSAT parameterizations, which was discussed in the previous slide, and then we created a surface storage called WCAP. The water from precipitation, the FSAT portion will go into these WCAP as inflow. The water stays in WCAP will evaporate at the potential rate called QEVAP. And then when the WCAP is filled, the water will leave the system as surface runoff. Now, we also need two spatially variant parameters to do this job. So if you remember, this FSAT MX value was set to 0.38 globally. Now we can use these maximum FSAT from the remote sensing data to prescribe the FSAT max on a regional scale. And also we can aggregate from a high resolution DEM map to generate a WCAP at 4 kilometer domain. We do these simulations, also run a 13 years offline simulations using the coldness forcing for two simulations. One we run is called no storage and then called no wetland. And the other is called the wetland simulations. So if we look at now, we're showing that the surface incorporating the surface wetland will reduce sensible heat and latent heat over the wetland dense region in the summer of the 13-year mean. And the change are compensated with each other and mostly focusing in the wetland dense area and northeast of the domain. This signal is also very important for the increase of ET in the wetland dense region. And also, if you scatter the delta ET, the wetland minus no wetland ET for the 3 months, across the FSAT max parameters and WCAP, we can see some interesting feature. There is almost an increasing a linear relationship between the FSAT max and the delta ET. However, this has a cutoff effect in a dry year, 2003, after 100 millimeters, indicating it is water limited. While in the wet year, you can see this linear effect can go to about 200 millimeters. And also you can see in the right that the WCAP has almost two peaks. One is about around 0 meters, and the next is about 7.5 meters, indicating that the shallow water or the medium depth of storage can stay longer and evaporate contribute more to ET in the 13-year mean and wet years. However, in dry years, as it is water limited, this signal is not as obvious. Finally, we do this, we incorporate the surface storage schemes to run the WOLF at 4 kilometer simulation for 3 summers. And as you can see, the 3 summers that the no wetland and wetland temperature and the no wetland and wetland precipitation, you can see for the temperature, there is almost a cooling effect for the wetland dense region, about 1 to 2 degrees, while in the precipitation wise, there's the impact is hard to tell. And basically, you can see a very strong impact on the southeast boundaries. It is very, we might want to consider enlarge the domain and some to get a robust conclusion. And finally, if we want to look at how this will impact on temperature compared to observation, you can see that the cooling effect induced by surface water will reduce the temperature bias around the wetland areas, about 1 to 2 degrees warm bias reduced. And finally, this is our conclusions, and thank you very much. We want to highlight that the wetland schemes will be important as comparing to these complex systems when we have an important implication for agriculture and ecosystems. Thank you very much, and thank you for questions.